This project, entitled Pilot Study for Integrating Microgrid and Distributed Renewable Energy Sources for an Electric Cooperative, is under Professor Carl Odulio from the UPEEE Institute. Project personnel include researchers from the academe and the industry. Our country, being situated in the Pacific Ring of Fire, is very vulnerable to natural calamities. We get around 20 or more typhoons every year. Along with typhoons, we also get other natural disasters that result in the disruption of our energy access. This not only affects the physical infrastructure of the country, it also hampers our economic system. In November of 2013, one of the worst typhoons in the last 30 years cost us around $10 billion. With all the disasters that our country is vulnerable to, there is a need to increase reliability, resilience, and security. These three can be addressed with the introduction of microgrid systems. An example of a microgrid configuration is shown in the image. Microgrids are normally designed to power critical loads or far-flung and island communities. They may be configured to operate with the main grid, but may continue to provide energy even if there is a fault in the main grid. This results in increased resiliency and reliability of the system, especially for critical loads. In developing microgrids, there are numerous options that are available when utilizing energy sources. The following examples may all be integrated in a microgrid, giving more flexibility in terms of technology, economy, and availability. This study's main objective is to improve the resilience of on-grid distribution networks, particularly those of the electric cooperatives, by enabling their standalone operation either as one microgrid or as multiple independent microgrids. Different assessment levels will be done on the target system, and the system design will follow. Dispatch and control algorithms will be developed for the target installation. The project's impact to society varies from system reliability and resiliency improvement to lower energy costs for the consumer and the promotion of clean energy. We have looked at the potential solar, wind, and hydroelectric energy sources that may be incorporated into the distribution utility. More than 2 gigawatt-hours per year of solar energy is available in the utility's franchise area. Almost 10 gigawatt-hours of wind energy is available. And around 17 gigawatt-hours of hydroelectric energy may be harnessed. We've also investigated load prioritization as part of the microgrid operations. Standalone operation of the microgrid may use these different levels to determine the required additional resources. These charts show the percentages of the different types of loads. Different scenarios have been developed for the microgrid operation, both in grid-connected and standalone modes. This determines the level of investments needed for a stable system under different conditions. A standalone microgrid that will serve 100% of the load will require the following resources using the different scenarios. We can see that having a grid-connected operation with sellback results in the lowest cost of energy. Operating with only the highest priority loads will require less resources and an even cheaper cost of energy. This, however, limits the loads served by the system in standalone mode. This is the resulting configuration if only the most critical loads are served in standalone operation. This will have the lowest level of investment required, but only about 8% of the total load will be energized. In looking at the system reliability indices, these are the resulting frequency and duration of the system interruptions. – Here's a chart of the reliability indices distribution. Resilience is analyzed by looking at the reliability of the system using only the critical loads. These are the results for the different priority levels. Here's a chart of the resiliency indices of the different loads. At the end of the project, we hope to develop the proper methodology that will help different utilities in analyzing their systems to convert them into microgrids where renewable resources may be integrated while operating in a stable and resilient manner.